yeah, thank you for the introduction, and I'm grateful to the organizers for the invitation. I really like visiting Poland, and it's always a nice opportunity. All right, so to introduce myself, I work in University of Groningen, very, very north of the, whoa, this is slow, of the Netherlands. That is my group over there. Yeah, some of my group members are here. Afion had a poster, and Edo is going to speak later in the session. What we do in our work, we perform calculations using state-of-the-art methods from computational chemistry. we calculate, we perform very accurate calculations of properties of atoms and molecules in the context of various fundamental problems in physics. Two main research directions are search for new physics with experiments that use atoms and molecules, test of the standard model, or searches for new physics. And the second one is predictions, very accurate predictions of spectra and properties of heavy elements, super heavy elements, and highly charged ions. And whatever we do, most of the work in our group is done in collaboration with experimental groups, which means that we have to supply uncertainties in our predictions, for example. All right. Yeah, I'll talk a lot about or not a lot, but I'll give an introduction to why we want to do these calculations. I'll talk about the methods that we use, and I'll give some examples of calculations which are relevant to this to the field of search for new physics. All right, motivation. We already had these searches mentioned earlier, but I'll give a bit of overview. Why do we want to look for physics beyond the standard model? And now I'm referring to experimental searches. Well, standard model is the best theory we have at the moment. It describes all of the known fundamental particles and 3 out of the 4 interactions. And so far, it's very good at explaining more or less everything we see, most things we see, and it also has strong predictive power, as we see from discovery of the Higgs boson. But this model is also incomplete, and there's some gaps in it. So one thing is it doesn't include general relativity. There is no theory of quantum gravity. A very big problem is the fact that according to the standard model, we should not exist, which is quite disturbing, I would say. Because, yeah, according to the standard model, we should have had the same amounts of matter and antimatter created, annihilated, and that's it. We would not be here. And also, standard model does not explain what can be dark energy or dark matter. Right? To address these gaps in the theory, there is new theories being proposed, extensions to the standard model, and this theory also invariably they predict new phenomena which has not yet been detected. For example, violation of fundamental symmetries, many orders of magnitude beyond prediction of standard model. So these predictions motivate experimental search. Why? On one hand, if you discover something great, you've discovered new physics, you're rich and famous, or just famous, and you confirm some theories. If you do not find anything, then it's also not, if you don't find anything, but you don't find anything in a good way, in the sense of setting an upper limit, that's also great. You might have ruled out some theories, or yeah, you're kind of one step closer to discovery, in a sense. All right. So in these experiments, one can search for new physics using accelerator experiments, huge facilities, many collaborations made of many people, or tabletop experiments with atoms and molecules, which is relevant here, of course. Why atoms and molecules? Well, we're looking for very, very small effects. Because, yeah, if they were bigger, they would have been already detected. And what happens is that electronic structure in atoms and molecules, in particular in molecules, acts as sort of an amplifier, bringing these effects into the measurable range. For example, we saw already today references to electric dipole moment of the electron, predicted to be 10 to minus 38 by the standard model, way too small for direct measurement. Other theories predict larger values by some orders of magnitude, still too small for direct measurements. But if we stick our electron in a polar molecule and try to measure there, there's the internal electric fields which amplify the effect by 5 orders of magnitude, bringing it into measurable range in a simplified picture. And this is true for many types of parity time violating properties, and we understand the model effects and parity violation as well. All right, so so that's the nice features of atoms and molecules for such experiments. They're sensitive because of the enhancements. They're versatile. We can use them to look for a whole zoo of different phenomena, parity violation, presence of EDMs of fundamental particles, even different types of dark matter. And these experiments are relatively small compared to accelerators and relatively cheap also compared to accelerators. Okay, yes, very interesting, very promising, but very challenging, as well, most experimental research is. But here we also need very, very high sensitivity to detect these tiny effects. Which means that these experiments require specially developed experimental techniques, but theoretical support can also be very crucial for their success. What can we do from the theory perspective? Well, since calculations should theoretically at least take less time than measurements, we can accompany experiment at all stages and provide support. We can understand how this phenomena on particle physics level, how it will affect electronic structure, how it will be translated into some measurable properties. We can identify promising candidates for measurements, systems that will be very sensitive to whatever we're looking for, but also which would have some experimental advantages. We can provide practical parameters for planning the experiment, predictions of transition energies, laser cooling schemes, and so forth. And also, all these experiments require parameters from electronic structure to interpret them. For example, if we're looking for parity time violating nuclear magnetic quadrupole moment, in the molecule, what we measure is energy shift or frequency shift or phase shift, and that can be translated back to this M through Wm, which is electronic structure coupling constant. These constants cannot be measured in principle and have to come from theory. So there it's also necessary to know these constants, and we need to calculate them. Right, if we want to carry out calculations in experimental context, these predictions should be reliable, they should be based on very accurate calculations, and we should be able to assign uncertainties on our results, because A, we want to, if we're providing predictions for planning measurements, we need to have some error range, of course. And also for interpretations, if we extract the uncertainties using our extract the effects using calculated theoretical values, then theoretical uncertainty goes into the uncertainty on the result. So we want to use a method which allows uncertainty estimation, which means that we need to select an appropriate method. So what we want to do, we want to solve the electronic Schrödinger or Dirac equation. Most of the theory that we heard here deals with much more complex systems. In this sense, we're lucky. We just have our nuclei and electrons. Nothing is colliding, nothing is being squeezed or anything. But of course, we cannot solve it exactly either. So we have different approximations which are made. And we have this landscape here, which describes the quality of ab initio electronic structure calculation. And the three parameters, relativity, electron correlation, and choice of basis sets, are parameters that determine the quality of any calculation. As we advance along each axis, then the quality of treatment of the corresponding parameter improves, but computational costs increase. And depending on what we're trying to achieve, what resources we have available, we should find ourselves somewhere in this landscape. So where are we? Well, we want to calculate the coupling constants, which are relativistic in nature. We want to deal with heavy systems, because in heavy atoms and molecules, sensitivity to new physics is enhanced. That means we have to use relativistic methods. We want to achieve high accuracy, so we need a method which is very powerful, which treats correlation very well, which should also be accompanied by a very large basis set. We want to be able to estimate uncertainties, which requires a method which is robust and transparent. So, in our case, our method of choice is the relativistic coupled cluster, which is considered the most powerful method for accurate treatment of heavy many electron systems. It's versatile. We have different variants of it. We have a variant which is suitable for ground states and closed shells. We have Fock space coupled cluster, which is multi-reference, where we can calculate a whole spectra. We can use specially developed relativistic basis sets, and this approach can be systematically improved, which allows us to assign uncertainties. So we go quite far on all the three axes, which gives us a very accurate method, but it's also very expensive. Accuracy comes at a price, and in our case, we pay the price of being able to treat only atoms or very small molecules. What is small? Between 2 and 6 atoms, let's say. Yeah, so what can we calculate? Well, whatever we want, whatever we need. We need atomic properties, energies, but also various parameters, hyperfine structure parameters, all kinds of molecular properties, these coupling constants that we need to interpret precision measurements. We can treat ground and excited states, and the accuracy expected is on the order of tens of milli-electron volts for energies, single percent for properties. But we can push this accuracy further to single milli-electron volt accuracy. And we can also set uncertainties through systematic investigations of computational parameters. And these two things, these are new kind of developments in my group in the last years. So how do we reach this milli-electron volt accuracy? Well, right, so let's say we perform a very high quality coupled cluster calculation, 4-component CCSD parenthesis T, very large basis set, decent active space, a calculation which would be considered golden standard of computational chemistry, which would be used to benchmark other calculations. And this will give us this accuracy of tens of milli-electron volts. Well, we can push the accuracy further. We can add higher order effects on each of the three axes. Perhaps we need to do it in a stepwise system using different programs, but we can do it. Yeah, for example, bright and QED corrections on the relativity axis, higher excitations and larger active space on the correlation axis. And we can augment our basis sets further and extrapolate it to complete basis set limit, which gives us the so-called platinum standard. So even better, and this is the best you can achieve for many electron systems, for heavy many electron systems. All right, how do we assign uncertainties? In computational chemistry, there is no clear prescription on assigning uncertainties, but there is a number of conceptual things we can do. We can calculate, let's say we calculate some property in a heavy system, and we want to know the error bars of our calculation. We can calculate the same property in a lighter homologue, where experiment is available, compare the result to experiment, use the discrepancy to set error bars on our predictions. Alternatively, we can calculate a different property in the same system where experiment is available and do the same thing, compare to experiment and use the error bars on the prediction. Or, and that's something we started doing in the last 2 years, set uncertainties based on incompleteness of the method. What does it mean? Well, we know in method like coupled cluster, we know which effects are included in our calculation. We know also which effects are missing because it's too computationally expensive or because there's no implementation available. But we can estimate the size of those missing effects and use that size in order to set the uncertainties. This is based on two assumptions. So first of all, that the size of higher order contributions diminishes very quickly with the order. For example, if we're talking about correlation, then triple excitations in coupled cluster procedure would contribute much more than any higher order excitations. So we can kind of take the highest included effects as estimate of everything that's missing on the corresponding axis. The second assumption that we make is that the different contributions are decoupled. They're virtually independent of each other, so we can combine them to total uncertainty as combination of independent effects. All right, so, and ideally, we do all three in parallel to get a sanity check and confirmation, of course. Right, so remaining, yeah, the introduction was very long, but I wanted to explain how we do the calculations, and I'll show some applications now. So first example is ionization potential of diatomic molecules, calcium fluoride, strontium fluoride, barium fluoride, and radium fluoride. These molecules were mentioned here many times already. I'll show how we evaluate uncertainty, how we reach this millielectron-volt accuracy, and also the predictive power of the method. Right, so the motivation here is actually radium fluoride. It's one of the first radioactive molecules which was already investigated extensively in the context of searches for new physics because of it has deformed isotopes and because it's very heavy. And this led to many experimental studies, including measurement of ionization potential, where we provided the theoretical predictions before the measurements. So we used couple cluster with higher order corrections. So this is our baseline extrapolated to complete basis set limit number. We added also higher order corrections to end up with the final result, which is, in fairness, not that different from where we start with, because different corrections also have different sign. Some of them cancel out. And we also have this uncertainty of 7 millielectron volts on the prediction. And this uncertainty was obtained by indeed evaluating different sources of uncertainty, basis set, which was also split into different contributions, correlation and QED, total uncertainty of 7 millielectron volts, with similar weights of the different sources. Okay, that's our result, that's our uncertainty. Well, how do we know that, well, that this makes sense at all? Right, so now we have the uncertainty that is assigned through computational study. We can do the first point on this list and see what happens in the lighter homologues, calcium fluoride, strontium fluoride, and barium fluoride, where experiment is available. Okay, we performed the same calculation in the lighter homologues. The results are shown here, and we have again the final results. We did the same corrections for the missing effects and estimated uncertainties as well. In this case, the uncertainties are even smaller, on the order of 3 millielectron volts, because these are lighter elements. Okay, for calcium fluoride and barium fluoride, accurate Rydberg spectroscopy is available, so we can compare our ionization potential in a blue circle to experiment, the blue square. And we see that we have excellent agreement with experiment with the results within the theoretical uncertainty of a few millielectron volts. So this confirms the accuracy of our method. For strontium fluoride, no such accurate experiment is yet available, so we hope that such measurements will be performed in the future. Okay, this was done by Sasha Kiberis, a former postdoc in my group. Now back to radium fluoride. So in the meanwhile, of course, our experimental colleagues have performed the measurements using two different ionization schemes, and they also came up with a number. In this case, we see that we have a good agreement with experiment, and the results certainly agree within the combined uncertainties of experiment and theory. In this plot, we can see how, first of all, this is a comparison of theory and experiment, the gray line for the different homologues. In this plot, we see how the gray line is the experiment with uncertainty, how improving the method improves the agreement with experiment towards the end. And of course, keep in mind that we have not seen the experiment when we were doing these calculations, so we get the right answer for the right reason, not through fitting or matching. Right, a small excursion into relativistic effects. We can look at the trends in the group. So for this for these molecules, the electron is removed from the s orbital of the metal. That means that, and we can see that from calcium fluoride to barium fluoride, the IP decreases because increasing principal quantum number means that the s orbital is expanded and it's easier to remove an electron. It's weakly bound. For radium fluoride, this trend is reversed because of relativistic contraction of the s orbital, which makes it harder to, which makes the orbital more stable, makes it harder to remove the electron. Right. With the same method, we also predicted the dissociation energy of the molecule, where the important thing to note here is that dissociation energy is higher than the IP, which means that one can actually excite this molecule to Rydberg states, which is useful for perhaps manipulating and controlling it without the molecule falling apart. Right, and this paper is now on archive and in review process. The experiment was led by Shen Wilkins from MIT. Okay, right. Last few minutes, I'm getting to the topic which was declared in my title, calculations of parity time violating coupling constants. And the first example is in framework of NL-ETM collaboration, which was nicely introduced by Joost before me. The aim is to measure the electric dipole moment of the electron with the cold and slow barium fluoride molecules. We see that, so the tiny prediction of the standard model, there's much larger predictions by new extensions. And every time we set a new upper limit, we rule out some of these extensions, or at least force the theorists to optimize their models anew. This best upper limit was set with hafnium fluoride plus. There is active experiment with terbium plus, as we heard today. And in our case, it's barium fluoride because of various experimental advantages. Right, so I don't need to describe the experiment that was done by Joost, but the point is that once the parity time violating energy difference, so in our case phase difference, is measured, in order to interpret it, we have this expression. So it would be due to two effects: the electric dipole moment of the electron, which is something that everyone hears about, and this kappa, which is another parity time violating effect, scalar pseudoscalar electron nuclear interaction. So there's actually going to be two effects entangled in this kind of measurement, which means that single measurement will not give us an unambiguous limit on the EDM of the electron, rather a combination of two effects. So we need multiple measurements. And any such measurements would require knowledge of WD and WS parameters to extract these effects from the energies. Right? So we have implemented a procedure to calculate these parameters using coupled cluster. And we use the same scheme to reach the highest possible accuracy to assign uncertainties on our predictions. We perform these calculations in barium fluoride because this is the system of interest for our collaborators. We see here a kind of visual representation of different sources of uncertainty, and we see that they differ between the different parameters. So for WD, the total uncertainty is higher, and it's dominated by relativistic effects. For WS, it's lower, and the composition is somewhat different. This stresses the fact that we need to evaluate uncertainties separately for different systems, different properties, and different states. We cannot use kind of a order of magnitude estimate. Oh, order of magnitude, yes, but we cannot use an umbrella estimate for uncertainty. Okay, these are the predictions in the end. So these are two numbers with uncertainties of a few percent. There were previous predictions on the low level of theory, and some also previous couple cluster predictions. This is could be considered the most accurate value for the moment, with the tightest error bars. And then we want to ask ourselves, okay, so how do we know whether this uncertainty that we set on our predictions, how do we know it's realistic? And we cannot go to this answer. We cannot calculate the same property in a light homolog because this property cannot be measured at all, this WD, WS parameters. But we can do something else. We can calculate a different property in the same system and compare it to experiment. The different properties should be selected wisely because it should be sensitive. It should kind of have the same computational behavior. It should be sensitive to the same effects. In this case, quality of description of the electronic function in the nuclear region is very important. So our proxy property then is magnetic hyperfine structure constants, which are also very sensitive to what's happening in the nuclear region. That is good. We calculated the parallel and perpendicular hyperfine structure of barium 137 and barium fluoride in the same molecule for good comparison. Yes, so we got uncertainty of about 5% on these predictions, but if we compare to experiment, we see that we actually do much better. We agree with experiment within the experimental uncertainty. Those gray squares are the experimental uncertainties, while blue lines are the theory error bars. So we perform, our uncertainties seem to be somewhat over-conservative. right? Yes, also these hyperfine structure predictions, they have strong predictive power. Calculations, they have strong predictive power. For example, we could also calculate hyperfine structure parameters of excited states, where not a lot of theory is being done on high accuracy level. Our colleagues measured hyperfine structure parameters of excited states due to in the barium fluoride, but hyperfine structure due to fluorine atom. So effect is much smaller, much harder for calculation because we're talking about excited states. And we're talking about small effects, so basis set and correlation are much more important. We see the difference in the size of error bars between the excited states and the ground state. But we also can see that still, even with the larger error bars, we're still in good agreement with the experimental values, which were measured by our colleagues from EDM collaboration. Last slide and I'm done. Good. And very recently, that was work done in the group of Tim Langen. Measurement of excited states of barium fluoride, the hyperfine structure constant due to barium 137. And again, we perform calculations, we assign uncertainties, and also end up in good agreement with the experiment. So we can also, which brings me back to the fact that we should also be able to trust our predictions for the coupling constants, which cannot be measured. All right. Yes. So this was this was recently submitted as 2 papers, theory and experiment. This work is now on archive. I was hoping I'd have time for this, but wasn't very optimistic. You should listen to the talk of Edu at the end of this session about parity variation in chiral molecules, something else we do. And with that, I'm done, I think.
Thanks a lot for this really nice talk. Questions?
Hello, very nice results.
Thank you.
I have a question regarding this active space, because you have active space up to 15 Hartree, if I remember correctly, and then how you estimate the inaccuracy due to this limitation in active space? Yes, because in principle, when you include all orbitals up to the, I don't know, 200 or 300 Hartree, probably there should be a little bit difference in energy, but I have no idea how it's sensitive.
No, it's a nice question, and it's not entirely straightforward. So first of all, if we start by correlating all the electrons, and if you do that, your virtual space should be kind of a mirror virtual space. So you need to go to a couple of thousands of Hartree. Yes, and then after we do that calculation, we perform calculation. Let's say we correlate everything to 2000 Hartree, then a test calculation where we correlate everything to 3000 Hartree. And usually there the changes are like 0.1% or something. So we can stop there basically.
Yeah, I have a question. May I? Okay. Can you say something about the importance of the Borschevsky effect for hyperfine structure? Do we know how large is the contribution in that context?
Yes. I'll be able to tell you much more in about 6 months because I'm going to Australia to work on that exactly. But in general, it's so for example, in precision measurements of cesium, one can probe it already. So, and with accurate calculations, you can calculate hyperfine structure with and without Borschevsky effect. And you can see this difference, so you can test it. I think it's like 1% or something. It's about 1 to 2%, if I'm not mistaken. But yeah, we're there, where we really need to look at it.
So when you're comparing with ionization potentials of molecules, and yeah, we were talking about molecules.
Yeah.
So what contribution does the uncertainty in the determination of the 0-point energy of the neutral and the ionized molecule play? Is that a big effect or is that small?
You mean the equilibrium geometry uncertainty in
Well, the 0-point energy.
Yeah.
The experiment is stuck with the 0-point energy. It has to.
Yeah.
It's not measuring the distance from the potentials. It's measuring.
No,
the
absolutely.
eigenstates.
So we can calculate the vibrational. We also calculate vibrational constants, and the uncertainty is also on order of 1% maybe, and that translates into the same uncertainty on the energy. So yeah, no, we provide the adiabatic IP with the accounting for zero. Yeah.
One more quick question. If not, let's thank our speaker again.